In the boundless expanse of a distant galaxy, billions of light years away from us, a star with a mass 100 times greater than our Sun is living its final moments. In a fleeting instant of its demise, it will unleash a colossal amount of energy, surpassing the combined energy of 1 trillion suns, generating shock waves that will ripple through the very fabric of space-time. Today, we embark on an extraordinary journey into the realm of cosmic phenomena so extreme that they challenge our understanding of reality. We will encounter explosions that outshine entire galaxies, black holes that relentlessly consume even light, and the fundamental forces that hold together the entire fabric of the universe. Prepare to face power beyond your wildest imagination, and so, our captivating exploration begins. Deep within every atom of your body, an invisible yet fierce struggle unfolds. Protons, tightly clustered in the nucleus, strive to instantly fly apart. Their positive electrical charges repel each other with immense force, much like two powerful magnets resisting attempts to bring them together. Yet, in an incomprehensible way, they are held in place, bound by the most powerful force in the universe. The strong nuclear force manifests over distances no larger than a proton, yet its power is truly boundless. Scientists estimate it to be 100 times stronger than electromagnetism and 100 trillion times more powerful than gravity. Imagine, if gravity were a faint whisper, the strong force would be a deafening clap of thunder, capable of shattering mountain peaks. This force is mediated by particles known as gluons, which act like invisible chains, binding quarks together to form protons and neutrons. The harder you try to pull these particles apart, the stronger the restraining force becomes. It's akin to stretching an elastic band that grows thicker and offers increasing resistance with every inch of extension. This astonishing phenomenon, known as confinement, means you can never isolate a single quark, no matter how much energy you apply. Inside each proton, 3 quarks perform their dance within a prison of pure energy. The gluons that bind them carry the strong interaction itself, creating an intricate web of interconnections that even the most advanced supercomputers cannot fully model. When you attempt to separate quarks, the energy you add merely creates new quarks and gluons. It's like trying to break a chain that instantly grows new links. The strong interaction operates at such minuscule scales that 1 femtometer seems like an enormous distance. A femtometer is 1 quadrillionth of a meter, a magnitude virtually impossible to visualize. At these distances, the familiar world of everyday physics ceases to exist. Space and time themselves become uncertain, governed by the peculiar laws of quantum mechanics. This force shapes the very building blocks of creation. It dictates which atomic nuclei can exist and which cannot. It sets the rate at which stars burn their nuclear fuel. It governs the balance between creation and destruction in the hearts of every star scattered throughout the cosmic void. Without the strong interaction, protons would instantly fly apart due to electromagnetic repulsion. Atomic nuclei would be unable to form. Nuclear fusion reactions in the cores of stars would never ignite. The universe would consist solely of hydrogen atoms and free electrons. However, despite its incredible power, the strong interaction also possesses a fatal weakness. Its action is confined to the atomic nucleus, which is roughly 1/10 trillionth the thickness of a human hair. Beyond this microscopic realm, other forces come into play. Let's transport ourselves to the vast universe, where distance plays a defining role, and witness the clash of gravity and light in the most powerful explosions ever recorded by humanity. Somewhere in cosmic space, a beam of pure energy pierces through space at nearly the speed of light. In just 10 seconds, it releases more energy than our Sun will produce over its entire 10 billion-year lifespan. This is a gamma-ray burst, the most powerful explosion the universe can generate. These cosmic titans arise when the most massive known stars collapse into black holes. We're talking about stellar giants whose mass ranges from 20 to 100 times that of the Sun, burning their nuclear fuel at an incredible rate that would deplete our Sun's energy reserves in just a few million years. When these behemoths finally exhaust their resources, gravity claims its ultimate victory. As the star's core relentlessly collapses, it ejects dazzling jets of matter and energy from its poles at an incredible speed, reaching 99% of the speed of light. The collapsing core gives birth to a nascent black hole, surrounded by a disk of superheated material, like a halo. Magnetic fields, distorted and amplified by the gravitational collapse, act like cosmic cannons, launching these jets outward with incredible precision. The jets pierce through the dying star like bullets through tissue paper, erupting outward as focused beams of destruction that maintain their tight collimation over vast distances. Imagine a laser beam that doesn't lose its focus, traveling from Earth to the nearest star. These jets accomplish something similar, but on scales millions of times larger, demonstrating incredible power and accuracy. A single gamma-ray burst can outshine 1 trillion stars, blinding an observer with its intensity. If the human eye could see gamma rays, these explosions would appear brighter than the full moon, even if they occurred in galaxies billions of light years away. The energy released in mere seconds exceeds what 10 trillion hydrogen bombs exploding every second for the entire existence of the universe could produce. The most powerful gamma-ray burst ever detected, dubbed BOAT, brightest of all time, occurred in October 2022. It was so intense that it overloaded gamma-ray detectors across the solar system and caused noticeable changes in Earth's upper atmosphere from a distance of 2 billion light-years. Imagine standing on Earth and seeing a flashlight beam from Alpha Centauri appear as bright as a car headlight. This gives you a sense of just how incredibly powerful these cosmic events truly are. The light we detect has traveled billions of years, carrying news of stellar deaths from a time when the universe was young and stars were more massive and turbulent than anything we see today. Scientists have found bursts so distant that their light began its journey when the first stars were born, less than 1 billion years after the Big Bang. These ancient beacons give us a glimpse into the early cosmos, when massive stars lived fast and died violently, seeding space with the heavy elements necessary for subsequent generations of stars and planets. But compared to what lurks in the darkness between galaxies, even these titans pale. At the heart of our galaxy lies a monster 4 million times more massive than the Sun, Sagittarius. A devours everything that dares to come too close, from gas clouds to entire star systems. Yet, this giant is considered small compared to the true titans of the cosmic depths. Some supermassive black holes contain the mass of 40 billion suns, compressed into an area smaller than our solar system. They are like cosmic vacuum cleaners with such intense gravity that nothing, not even light, can escape once it crosses their event horizon. Space and time warp around them like water swirling down a drain, creating distortions that would seem impossible if we weren't observing them directly. These gravitational monsters did not grow slowly. The most distant quasars shine from a time when the universe was less than 1 billion years old, powered by black holes that somehow grew to billions of solar masses in the cosmic equivalent of a few minutes. How they achieved such impossible growth remains one of astronomy's greatest mysteries. Ordinary stellar evolution simply cannot explain their existence. The leading theory suggests that these giants began as massive seeds, formed directly from collapsing gas clouds in the early universe. Unlike stellar mass black holes, which form from dying stars, these primordial monsters could have contained hundreds of thousands of solar masses from their birth. Such an early start allowed them to grow rapidly, accreting surrounding matter and merging with other black holes. Supermassive black holes, these cosmic giants, not only devour everything around them, but also interact with other black holes, forming complex cosmic dances. As gas plunges into the abyss of a supermassive black hole, colossal friction heats it to unimaginable temperatures, reaching millions of degrees. This superheated material forms an accretion disk that shines brighter than 100 billion stars combined. The disk spins at such incredible speeds that matter at its inner edge moves at velocities comparable to the speed of light, experiencing time dilation effects that would stretch seconds into hours for external observers. The brightest quasars, powered by active black holes, are visible from the most remote corners of the observable universe, like cosmic lighthouses broadcasting their presence across billions of light years. They outshine the entire galaxies in which they reside, making the light of hundreds of billions of stars seem dim in comparison to their dazzling brilliance. But that's not all. The most aggressive black holes eject jets of particles moving at nearly the speed of light, creating beams that stretch for hundreds of thousands of light years. These jets carry enough energy to transform entire galaxies, heating gas clouds to millions of degrees and suppressing the formation of new stars in vast regions of space. These cosmic energy streams can remain active for millions of years, continuously saturating the surrounding environment with colossal power. However, recent observations have revealed black holes whose masses appear excessive for the galaxies they inhabit, disrupting the usual correlations between the mass of the central black hole and galactic properties. These supermassive giants challenge our understanding of how galaxies and their central black holes co-evolve, forcing scientists to revisit existing theories and seek new explanations. But even these titans of the cosmos are subject to forces acting on scales beyond all imagination. Across 13,800,000,000 light-years of space, an invisible force is winning a cosmic war. Every second, it pushes galaxies apart, stretching the very fabric of space-time. This mysterious force, dubbed dark energy, accounts for 70% of everything that exists. And yet, we know almost nothing about its true nature. Dark energy is unlike any other known force. It does not weaken with distance, like gravity or electromagnetism. Instead, as space expands, more dark energy fills the void. The larger the universe becomes, the faster it expands. It's like a cosmic gas pedal that only knows how to accelerate, growing more powerful as it pushes everything apart. Scientists discovered this force purely by accident while studying distant supernovae in the 1990s. They had assumed that the expansion of the universe was slowing down due to the gravitational pull of all the matter within it. To their surprise, however, they found the opposite. Today, space is expanding faster than it was billions of years ago, as if an invisible hand is pushing everything apart with increasing force. Imagine the universe as a balloon being inflated by an invisible breath. Dark energy is that breath, causing every point on the balloon's surface to move away from every other point. Galaxies drift in this expanding space like boats in a turbulent ocean, unable to resist the tide carrying them into the cosmic depths. The amount of dark energy in the universe increases as space expands. This, at first glance, violates the law of conservation of energy, one of the most fundamental laws of physics. Nevertheless, observations consistently show that the energy density of dark energy remains constant, even as the volume of space increases. Where this additional energy comes from remains completely unknown. Current theories suggest that dark energy could be a property of space itself, a kind of cosmic constant that Einstein initially proposed and then called his greatest blunder. Other scientists believe it could be a dynamic field that changes over time, or even evidence that our understanding of gravity needs a serious revision on cosmic scales. The implications of dark energy are profound and terrifying. In the distant future, it will rip apart everything we see. First, galaxy clusters will disintegrate beyond recognition, becoming isolated islands in an ocean of expanding darkness. Then, individual galaxies will lose their ability to hold together, unable to resist the cosmic expansion. And finally, even atoms themselves could be torn apart in a process scientists call the Big Rip. The moment some scientists call the Big Rip is approaching, stars shining in the night will one by one cease to exist. Planets orbiting their suns will be cast into the abyss of cosmic space. Even the smallest particles that make up all matter will be separated by unimaginable distances. Dark energy, now seemingly harmless, will become the absolute destroyer of the universe, annihilating everything that gravity and other forces created over billions of years. Imagine taking an entire mountain and compressing it to the size of a tiny sugar cube. Even in that state, this object would be 1,000 times less dense than a neutron star. These cosmic beacons manage to pack the mass of our Sun into a sphere just 12 meters in diameter. This generates gravitational fields so powerful that they distort light itself and warp space-time, creating inconceivable geometric figures. However, gravity is far from the most frightening feature of these celestial bodies. Neutron stars possess magnetic fields that are 1 trillion times stronger than Earth's protective magnetosphere. These invisible force fields capture charged particles and accelerate them to nearly the speed of light, creating beams of radiation that pierce through space like cosmic searchlights, powered by the fundamental forces of the universe. The magnetic field of a typical neutron star is so powerful that it could wipe all data from credit cards on Earth from a distance of 600 meters. If you could somehow get within about 1,000 kilometers of it, the magnetic force would be so immense that it would pull the iron from your blood. The field lines themselves become visible as they trap and channel streams of charged particles into narrow beams. As these magnetized neutron stars rotate, they become pulsars, emitting beams of radio waves and X-rays with the precision of an atomic clock. Some spin 600 times per second, faster than a kitchen blender, yet maintain perfect synchronization, surpassing the most accurate clocks ever built by humans. Each pulse marks another rotation of the stellar corpse, spinning in the utter darkness. The surface of a neutron star is a world of impossible physics, where familiar matter cannot exist. The magnetic field is so strong that it stretches atoms into needle-like shapes aligned along the field lines. The usual atomic structure is completely destroyed, giving way to exotic forms of matter not found anywhere else in the universe. Any ordinary matter falling onto the surface of a neutron star is instantly compressed into a layer just a few millimeters thick. Gravity is so intense that a marshmallow dropped from waist height would hit the surface with a force comparable to a hydrogen bomb explosion, releasing more energy than all the explosives used in World War II. Some neutron stars, known as magnetars, possess magnetic fields that are 1,000 times stronger still, approaching the ultimate strength allowed by the laws of physics. When these objects undergo magnetic quakes, their crust cracks and shifts, releasing more energy in 1/10 of a second than our Sun produces in 100,000 years. These magnetic cataclysms generate gigantic flares that can be detected across the galaxy. The most powerful magnetar flare ever recorded temporarily affected Earth's upper atmosphere from a distance of 50,000 light-years, demonstrating the incredible reach of these stellar remnants. The magnetic field around a magnetar is so intense that it affects the vacuum of space itself, causing it to become birefringent, similar to a crystal. Light waves become polarized as they pass through this magnetized void, providing astronomers with direct evidence of field strengths exceeding anything achievable in Earth laboratories. However, these stellar remnants are just the beginning of nature's most extreme creations. Invisible threads stretch across the observable universe, capable of slicing planets like wire through cheese. These cosmic superstrings, if they truly exist, are one-dimensional objects, thinner than a proton, yet potentially longer than galaxy clusters. They are scars left over from the birth of the universe, marking phase transitions in the fundamental structure of space-time. Cosmic strings are hypothetical one-dimensional defects in the fabric of space-time. According to string theory, cosmic strings emerged in the universe's first moments after the Big Bang, when it underwent rapid changes in its fundamental properties. They can be compared to cracks on the surface of a frozen pond, marking the boundaries between regions that crystallized with slight differences as the cosmos cooled from an initial state of absolute symmetry. Despite the fact that 1 meter of a cosmic string could weigh as much as our entire planet, these objects remain so thin that they are effectively one-dimensional. They possess length but lack width and height in the conventional sense. They balance on the edge between existence and non-existence, matter and energy, reality and pure mathematical abstraction, manifesting as a unique phenomenon. The energy contained within a cosmic string is practically unimaginable. A segment of string stretching from Earth to the Moon would hold enough energy to power human civilization for trillions of years. Yet, this colossal energy is concentrated in such an infinitesimally thin line that its thickness is immeasurable, making cosmic strings the ultimate embodiment of energy density. The movement of cosmic strings through space causes ripples in the very fabric of space-time, generating gravitational waves that can be detected by the most sensitive instruments. These waves would possess unique characteristics, distinct from those arising from black hole mergers or neutron-star collisions, allowing scientists to confirm the existence of these theoretical objects. When two cosmic strings intersect, they can form loops that begin to oscillate like guitar strings plucked by the hand of the universe itself. However, instead of sound waves, these vibrating loops create distortions in the fabric of reality, generating gravitational waves that propagate in all directions at the speed of light. These cosmic string loops gradually lose their energy by emitting gravitational waves, and over time, they shrink until they finally disappear. A loop the size of our solar system would release all its energy in just a few million years, ending its existence in a powerful burst of space-time distortion. There are speculations that cosmic strings could function as cosmic highways, enabling superluminal travel through warped space. If 2 points in space were connected by a cosmic string, it would theoretically be possible to traverse along that string and reach a destination faster than light traveling through ordinary space. This would make cosmic strings the most efficient cosmic shortcuts in the universe. Other theories suggest that cosmic strings might serve as windows into extra dimensions hidden from our three-dimensional world. Strings could be fundamental objects existing in higher dimensional space, with only their one-dimensional cross-sections visible in our reality. These theoretical objects currently remain hidden within the mathematical models of physics, awaiting their discovery or refutation through future observations. 4 billion light-years from Earth, a black hole the size of our solar system ejects a powerful stream of particles that spans an entire galaxy. This superheated plasma stream moves at 99.9% the speed of light, carrying enough energy to power a trillion stars while maintaining perfect focus over distances that defy human comprehension. Quasar jets arise in the chaotic environment surrounding supermassive black holes, where space-time itself becomes a battleground between gravity and magnetism. As matter spirals towards its inevitable doom, it forms an accretion disk spinning at incredible speeds. Magnetic fields, amplified by the disk's rotation, become twisted, accumulating immense amounts of energy. These magnetic field lines act as cosmic particle accelerators, channeling matter from the inner regions of the accretion disk into narrow beams that erupt from the black hole's poles. In this way, gravitational forces, which seemingly should absorb everything, instead eject a portion of matter back into space at relativistic velocities, utilizing this magnetic catapult mechanism. In the boundless reaches of space, phenomena of astonishing power and beauty exist. One such marvel is the jets emanating from the vicinity of supermassive black holes located at the cores of active galaxies, or, more simply, from the heart of a magnetic catapult. These streams of matter are so perfectly straight that they appear to have been drawn with an ideal instrument, as if a divine hand had traced a line across cosmic space. They maintain their narrow focus over distances reaching hundreds of thousands of light years, piercing the universe with precision unattainable by terrestrial technology. The collimation of these jets is so perfect that when observed with radio telescopes, they appear as the thinnest threads, even from billions of light years away. The particles comprising these jets possess energies millions of times greater than what can be created in the most powerful particle accelerators built by humans. Individual protons hurtle along the jet at velocities approaching the speed of light, their relativistic mass increasing thousands of times, transforming ordinary matter into cosmic projectiles of incredible destructive power. When such a jet, emanating from a quasar, is aimed directly at Earth, astronomers observe a blazar. Its light flickers and changes brightness like a lighthouse beam sweeping past an observer. A blazar's brightness can vary by hundreds of times within days or even hours, as turbulence within the jet creates bright knots of emission moving towards our planet at apparent superluminal speeds. However, this superluminal motion is merely an optical illusion arising from the geometry of observation. When matter moves at 99% the speed of light almost directly towards an observer, it appears to cover colossal distances in an unimaginably short time. This effect vividly demonstrates how close to the absolute speed limit these cosmic jets are actually moving. The most powerful quasar jets possess enough energy to heat entire galaxy clusters, blowing enormous bubbles in the surrounding gas that persist for hundreds of millions of years. These cosmic blowtorches can suppress the formation of new stars in regions spanning millions of light years, effectively sterilizing colossal volumes of space. Recent observations have revealed jets extending far beyond their host galaxies, penetrating the intergalactic medium, where they continue to propagate for millions of years. These ancient jets carry the imprints of black hole activity from the early epochs of the universe's existence, when it was far more turbulent and dynamic than it is today. In a binary star system located 30 million light-years away, a white dwarf star slowly siphons matter from its companion, like a cosmic vampire feeding on stellar blood. Over millions of years, hydrogen gas flows from the larger star to the compact remnant, accumulating layer by layer, much like snow piling up on a mountainside. However, this stellar snowball is approaching a critical point that will trigger one of the most precise and powerful explosions in the universe. White dwarfs are dense cores left behind after sun-like stars exhaust their nuclear fuel and shed their outer layers. These stellar remnants compress a mass comparable to our Sun into a sphere the size of Earth, creating matter so dense that a teaspoon of it would weigh as much as a car. The surface of white dwarfs is heated to tens of thousands of degrees, hot enough to vaporize any known material. The matter stolen by the white dwarf accumulates on its surface, compressed by gravity into a thin shell of hydrogen, where pressure and temperature gradually build. The white dwarf acts like a cosmic pressure cooker, slowly heating this stolen material till nuclear fusion ignites in the surface layers. When the white dwarf's mass reaches 1.4 times that of our Sun, a catastrophic event occurs. This critical mass, known as the Chandrasekhar limit, represents the maximum weight that degenerate electron pressure can support. Exceeding this limit, the star can no longer resist its own gravity. The accumulated material ignites in an uncontrolled thermonuclear explosion that rips the star apart in mere seconds. The explosion propagates through the white dwarf like a flame front engulfing cosmic dynamite, transforming carbon and oxygen nuclei into iron and nickel through explosive nuclear fusion. The star literally burns itself out. The dying star burns itself to the ground, giving rise to a Type Ia supernova, one of the most precise yet violent phenomena in the universe. Each such supernova releases virtually an identical amount of energy, as they all involve a similar mass of matter engaged in the same nuclear reaction. This cosmic standardization makes them indispensable tools for measuring colossal distances spanning billions of light years. The explosion blinds with its light, reaching a brightness of 5 billion suns, and is discernible from galaxies many billions of light years away. For several weeks, a single exploding white dwarf star can outshine an entire galaxy containing hundreds of billions of ordinary stars. The brightness rapidly peaks and then gradually fades over several months as the radioactive elements produced by the explosion decay and release their energy. This explosion synthesizes and disperses across vast regions of space the elements that are the foundation of life. The calcium in our bones, the iron in our blood, and the nickel in our coins, all were created in the hearts of exploding white dwarfs. Literally, every human being is made of stardust, scattered by these cosmic crematories billions of years ago. The shockwave from a Type Ia supernova propagates outward at speeds reaching thousands of kilometers per second, heating the surrounding gas to temperatures of millions of degrees. The explosion can initiate new waves of star formation in nearby gas clouds, simultaneously enriching them with the heavy elements necessary for planet formation. Two city-sized objects, neutron stars, are locked in a gravitational dance of death lasting millions of years. The collision of these crushed cores of massive stars will unleash the most violent event in the universe, creating elements more precious than all the treasures of the world. Each neutron star possesses a mass greater than the Sun, yet compressed into a sphere just 12 meters in diameter. Their surfaces consist of atomic nuclei packed so densely that a teaspoon of this substance would weigh 6 billion tons on Earth. These are not ordinary objects, but rather the densest forms of matter capable of existing without collapsing into black holes. As they draw closer, the neutron stars deform each other's shapes under the influence of gravity. Tidal forces stretch and squeeze these incredibly dense objects, generating heat that causes their surfaces to glow at temperatures of millions of degrees. Their orbital motion accelerates as energy radiates away through gravitational waves. These waves carry away orbital energy at an ever-increasing rate, causing the neutron stars to spiral closer together, faster and faster. The waves themselves are ripples in space-time, stretching and compressing the fabric of reality as they propagate at the speed of light. Modern detectors on Earth can measure these waves, even though they change distances by less than 1/10,000th the width of a proton. In the final seconds before impact, the neutron stars complete hundreds of orbits per second, spinning around each other faster than a helicopter blade. The gravitational waves they generate become so powerful that they carry away energy equivalent to 3 solar masses in just the last few seconds before the collision, causing an exponential acceleration of the death spiral. When neutron stars collide, a short burst of gamma rays occurs, followed by a longer explosion called a kilonova. The collision is so violent that it shakes the universe, sending gravitational wave signals that can be detected from billions of light years away thanks to sensitive instruments. The merger produces elements heavier than iron through a process known as rapid neutron capture. In the extreme conditions of the collision, atomic nuclei are bombarded with so many neutrons that they barely have time to absorb them. This creates unstable neutron-rich isotopes that decay into stable heavy elements such as gold, platinum, and uranium. Neutron star collisions are cosmic factories for producing valuable elements like gold, platinum, and uranium. A single such merger can produce an amount of gold comparable to several Earth masses, as well as significant volumes of other precious metals. This stellar treasure is ejected into the surrounding space at speeds reaching 1/3 the speed of light, enriching it with materials that will later become part of new generations of planets and asteroids. The ejection of matter occurs in several stages, with different components moving at varying speeds. The fastest particles form the initial gamma-ray burst, while slower components create expanding shells that emit light from radioactive decay for several weeks after the collision. This kilonova glow arises from the decay of billions of newly formed atomic nuclei, creating a fireball with a brightness comparable to hundreds of millions of suns. 13.8 billion years ago, our entire known universe was compressed into a point smaller than a proton. All matter and energy, from the smallest quantum particles to vast galaxy clusters, occupied an infinitesimally small space. This was the singularity of the Big Bang, the ultimate manifestation of cosmic power, the moment existence itself began. At this moment of genesis, the laws of physics as we know them ceased to apply. Temperature and density reached infinite values. Space and time lost all meaning. The 4 fundamental forces governing everything in the modern universe were unified into a single, incomprehensibly powerful interaction that defined reality itself. In the first, infinitesimally small fraction of a second, when light wouldn't even have had time to cross a proton, the universe expanded at a speed exceeding the speed of light. This period of cosmic inflation stretched space billions of times in less than the blink of an eye. Space did not explode into an already existing void, but rather created new space as it grew, carrying matter and energy along with it. The temperature in those first moments was so high that even the fundamental forces of nature could not exist separately. Gravity, electromagnetism, the strong and the weak nuclear forces were indistinguishable manifestations of a single superforce that existed only in the first moments of creation. As the universe expanded and cooled, this cosmic unity broke apart, much like glass cooling too quickly. The forces separated in a series of phase transitions, releasing vast amounts of energy and defining the structure of physical laws. First, gravity separated, then the strong interaction, and finally, electromagnetism separated from the weak interaction. Within the first minute after the Big Bang, the universe cooled enough for the first atomic nuclei to form in a process called Big Bang nucleosynthesis. Protons and neutrons, formed from cooling quarks, fused in a cosmic crucible, creating most of the hydrogen and helium we observe today. The energy density was so great that matter and antimatter constantly annihilated each other, erupting into pure energy. For 300,000 years after the Big Bang, the universe remained opaque to light. Free electrons scattered photons so intensely that light could travel only negligible distances before being absorbed and re-emitted. The cosmos resembled a glowing fog filled with energy but impenetrable to sight. Then came the cosmic dawn. Electrons and atomic nuclei finally combined to form the first neutral atoms, allowing light to travel freely for the first time. This cosmic enlightenment created the afterglow we observe today as the cosmic microwave background radiation, a faint echo of creation itself, filling every corner of the sky. Every corner of the celestial vault is illuminated by the afterglow of cosmic events. The Big Bang is believed to have been not merely an ordinary explosion occurring in some space, but an explosion of space itself. This event gave birth to time, matter, and established the physical laws governing all processes, from the smallest quantum fluctuations to the formation of giant galaxies. No event before or since can compare to the power of the Big Bang, which created everything from nothing and laid the foundations for the universe's existence. However, even this epical cosmic birth may not be the ultimate expression of power in the universe. Beyond ordinary supernovae, something far more destructive lurks. When a star 50 times more massive than our Sun exhausts its nuclear fuel, it doesn't just collapse and explode. Instead, it generates a hypernova, an explosion of colossal energy that surpasses ordinary supernovae by 10 to 100 times. A hypernova releases energy equivalent to billions of atomic bombs detonating every second for millions of years. These stellar monsters are extremely rare, even by cosmic standards. Only the most massive stars in the universe, possessing rapid rotation, are capable of triggering a hypernova at the moment of their death. The combination of extreme mass and rotation creates such violent conditions that an ordinary stellar death cannot contain the fury about to be unleashed. Upon the collapse of such a star's core, a black hole forms almost instantaneously. However, the star's rapid rotation prevents a simple, symmetric collapse. Instead, the infalling matter forms an accretion disk around the nascent black hole, spinning so rapidly that it transforms into a cosmic dynamo, generating magnetic fields of unimaginable strength. These twisted magnetic field lines act like springs stretched to their limit. When they finally snap and reconnect, they eject jets of matter and energy at speeds reaching 99.9% of the speed of light. These jets pierce through the collapsing star like cosmic drills, carrying enough energy to power our Sun for billions of years. The jets bore through the star's outer layers and erupt into cosmic space, creating gamma-ray bursts that can be detected from billions of light years away. But the violence doesn't end there. The shock wave from the jet's passage heats the star's interior to temperatures exceeding those in the cores of ordinary stars, triggering explosive nuclear burning throughout the stellar remnant. Layer by layer, the star explodes outward in a cascade of thermonuclear violence. Carbon turns into neon, neon into silicon, and silicon into iron in a matter of seconds. The energy released by these rapid fusion reactions adds to the destruction, creating an explosion that can be seen from the edge of the observable universe. A single hypernova can synthesize more heavy elements than dozens of ordinary supernovae. The extreme conditions produce radioactive isotopes that decay over weeks and months, fueling an afterglow that persists long after the initial explosion. These cosmic forges create many of the elements necessary for life, scattering them across vast regions of space. The most powerful hypernovae can disrupt star formation processes in entire galactic regions. Their shockwaves compress nearby gas clouds, triggering new waves of stellar birth, while simultaneously heating the surrounding environment to temperatures that prevent further star formation for millions of years across hundreds of millions of light-years of space. Two massive galaxy clusters are hurtling towards each other at thousands of kilometers per second. Each cluster contains thousands of galaxies, trillions of stars, and vast amounts of superheated X-ray emitting gas. When these cosmic titans collide, they generate the most energetic events in the universe since the Big Bang. Galaxy clusters represent the largest gravitationally bound structures in the cosmos. The Coma cluster alone contains over 1,000 galaxies and has a total mass equivalent to 100 trillion suns. When clusters of such magnitude collide, the energy released surpasses the combined power of all stars in both clusters by millions of times. In the vast expanse of space, where galaxies dance in a gravitational waltz, colossal collisions of galaxy clusters occur, their mass exceeding that of the Sun by millions of times. This cosmic cataclysm unfolds slowly, by astronomical standards, as the clusters approach each other over hundreds of millions of years. Dark matter, the mysterious substance that constitutes the bulk of each cluster, is subject only to gravitational attraction and passes unimpeded through the collision site. However, the hot gas filling the intergalactic medium awaits a completely different fate. At the moment of cluster merger, gas clouds collide head-on at dizzying speeds, reaching 5,000 kilometers per second. This collision generates powerful shock waves that heat the gas to temperatures exceeding 100 million degrees Celsius, hot enough to strip electrons from atoms. The resulting plasma glows in the X-ray range, forming some of the brightest objects in the universe. These cosmic collisions can initiate the formation of radio halos, extending for millions of light years. Magnetic fields, distorted and amplified by the collision, accelerate electrons to nearly the speed of light, causing them to emit radio waves as they spiral around the field lines. This results in ethereal radio emission, dwarfing entire galaxies in size. The most violent cluster collisions create bow shock waves that propagate outward at thousands of kilometers per second. These cosmic sonic booms compress and heat the surrounding medium, forming structures discernible over vast distances. The energy contained within these shock waves surpasses the combined energy of billions of supernovae. During the collision, individual galaxies within the clusters experience their own, no less violent, encounters. Tidal forces can strip stars from the outskirts of galaxies, creating long streams of stellar debris that trace the cluster's gravitational dance. Some galaxies may be completely destroyed, their stars scattered into the expanding cluster halo. The collision can also trigger massive bursts of star formation as gas clouds within galaxies are compressed during the impact. These bursts can increase a galaxy's star formation rate by hundreds of times, forming bright blue regions filled with newly born massive stars destined to live fast and die young. However, beyond these grand yet relatively harmless cosmic phenomena, a threat capable of instantly ending all existence lies hidden in the depths of the quantum foam that underlies reality. The Higgs field, which gives all particles mass, may not be in its minimum energy state. If this field suddenly transitions to its true minimum state, a bubble of destruction would emerge, expanding at the speed of light, rewriting the laws of physics and annihilating everything in its path. The Higgs field permeates every corner of space, existing even in the vacuum between atoms. Like a ball balanced atop a hill, this field can reside in a state known as a false vacuum. It appears stable, but could potentially roll down to an even lower energy level, fundamentally changing the nature of reality itself. If vacuum decay were to begin anywhere in the universe, it would spawn an expanding sphere of true vacuum, moving outward at the speed of light. Nothing could escape this cosmic wave of destruction, as no information or matter can travel faster than light. We would have no warning of its approach until the very moment of its arrival. Inside the bubble of true vacuum, the fundamental constants of nature would be different. Particles might possess different masses or not exist at all. Atoms, as we know them, would be unable to form. The strong nuclear force could weaken, leading to the instantaneous disintegration of all atomic nuclei. Chemistry and biology would become impossible. The energy difference between the false and true vacuum would be released as the bubble expands. This energy could surpass the rest energy of all matter in the universe, making vacuum decay more powerful than converting every proton, neutron, and electron into pure energy. The universe would be flooded with energy exceeding that of all stars and galaxies combined. Current calculations indicate that the vacuum we inhabit may be in a metastable state, balancing on the verge between stability and decay. Energetic events such as cosmic ray collisions or the process of black hole evaporation could potentially trigger this transition. Even quantum fluctuations can spontaneously generate a bubble of true vacuum in the very heart of the void. The terror of vacuum decay lies in its inevitability if a false vacuum state truly exists. Quantum mechanics relentlessly asserts that any metastable state will eventually decay, even if the probability of this event is infinitesimally small. On the scales of cosmic evolution, spanning unimaginable stretches of time, even the most improbable events become inevitable. Vacuum decay would be the ultimate cosmic reset button that would bring all existence to an end. Every star, every planet, and every living creature would be erased from the face of the universe, making way for a new reality with entirely different physical laws. Not a single trace of our current world would remain, not even the memory of its existence. Some theoretical constructs suggest that vacuum decay may have occurred repeatedly throughout our universe's history, with each transition giving rise to new regions with unique physical laws. Perhaps we inhabit just one of many bubbles, surrounded by regions where the rules of existence seem utterly alien. In the first moments after the Big Bang, when the universe was smaller than an atom and denser than a neutron star's nucleus, tiny density fluctuations could have led to the formation of black holes with masses exceeding that of mountains, yet smaller than atoms. These primordial black holes would possess gravitational fields of such colossal strength that they would warp space and time to scales invisible to the human eye. Unlike black holes formed from collapsing stars, primordial black holes could have had absolutely any mass. Some might have weighed as much as an ordinary paperclip, while others could have surpassed the mass of our sun. The tiniest of them would represent quantum objects, where the peculiar laws of quantum mechanics clash with the undeniable authority of general relativity, forming phenomena we can barely comprehend. A primordial black hole with the mass of a mountain would be smaller than a proton, yet its gravitational field would be millions of times stronger than anything we can create on Earth. Space and time around such objects would be warped into unimaginable geometric forms, giving rise to regions where familiar concepts of distance and time lose all meaning. These microscopic monsters may be among the most violent objects in the universe. According to Stephen Hawking's calculations, black holes emit radiation and gradually evaporate over time. The smaller the black hole, the faster it evaporates and the more dramatic its demise. A primordial black hole with a mass comparable to a large asteroid would explode with energy equivalent to millions of hydrogen bombs. The final moments of a small primordial black hole's life would be incredibly spectacular. As it shrinks to subatomic sizes, the evaporation rate increases exponentially. In the last second of its existence, it would release more energy than our sun produces in an entire year. And all this energy would be concentrated in a point smaller than an atomic nucleus. If primordial black holes exist in sufficient numbers, they could hold the key to one of cosmology's greatest mysteries, the nature of dark matter. These invisible objects would exert gravitational influence without emitting light, precisely matching the properties astronomers observe for dark matter scattered throughout the universe. The search for primordial black holes has led scientists to investigate the most extreme environments in space. When these objects pass through stars, they heat the stellar material and cause noticeable changes in brightness. When colliding with neutron stars, they can generate gravitational waves that can be detected by modern instruments. Some primordial black holes could have grown in size over cosmic epochs, accreting matter and merging with other black holes. These objects might be lurking in the dark corners of the cosmos, having evolved into invisible predators, awaiting the moment they can consume a new portion of matter. Their gravitational lensing could occasionally distort and magnify light from distant stars. Primordial black holes possessing colossal mass could have been the starting point for the formation of the supermassive black holes currently observed at the centers of galaxies. This would resolve the question of how such large black holes could have formed in the early stages of the universe's existence, when ordinary stellar evolution was just beginning. Even before the universe was 1 second old, space underwent the most rapid expansion in cosmic history. In a period of time less than that required for a light beam to cross a proton, the universe expanded from a size smaller than an atom to larger than a grapefruit. This process, known as cosmic inflation, is the most powerful force ever unleashed, stretching space at superluminal speeds and setting the stage for everything that followed. During inflation, space expanded by at least 10 to the power of 26 times in just 10 to the power of minus 35 seconds. To put this into perspective, imagine a single atom suddenly becoming larger than our solar system in less time than it takes light to cross the width of that atom. This expansion was so rapid that it defies human comprehension. The driving force behind inflation was a quantum field called the inflaton, which filled all space with immense energy density. Unlike ordinary matter, this field possessed the unique property of generating more energy as space expanded, acting like a cosmic fuel that never ran out. The larger the universe became, the more energy became available for further expansion. Inflation solved several fundamental problems that had puzzled cosmologists for decades. Before inflation, the universe would have been filled with exotic particles and topological defects that should be observable today. The rapid expansion stretched these objects to sizes exceeding the observable universe, effectively hiding them beyond our cosmic horizon. The expansion during inflation was so extreme that regions of space that were initially in contact were stretched far beyond any possibility of interaction. This explains why the cosmic microwave background radiation has virtually identical temperatures in all directions. Although these regions could never exchange energy after the expansion began, quantum fluctuations in the inflaton field during inflation were stretched to cosmic scales, creating density variations that later evolved into galaxies and galaxy clusters. These minuscule fluctuations in the fabric of space-time became the seeds for all large-scale structure in the universe, from the smallest stars to the largest superclusters. The amount of energy involved in cosmic inflation was truly astonishing. In just a tiny fraction of a second, the inflaton field released more energy than has been produced by every star in the observable universe over the past 13.8 billion years. This energy went into creating new space and filling it with the matter and radiation we see now. When inflation finally ended, the inflaton field decayed into ordinary matter and radiation, reheating the universe to temperatures exceeding 10 to the power of 28 degrees. This was hot enough to create and destroy particles at speeds that would make the cores of the most massive stars seem icy in comparison. Some theories suggest that inflation did not happen just once, but is an eternal process that continues to create new regions of spacetime beyond our observable universe. In this scenario, our entire universe may be just one bubble in an infinite multiverse, where new universes are constantly being born through inflation. At the core of a dying star, spinning at 1,000 revolutions per second, magnetic fields 1 trillion times more powerful than Earth's are about to unleash destruction beyond imagination. This is a magnetorotational supernova, where the combination of extreme rotation and magnetic force creates explosions that eclipse even the most powerful gamma-ray bursts, generating magnetic fields so intense they could tear atomic nuclei apart at distances of thousands of kilometers. When the largest stars in the boundless expanse of the universe reach the end of their lives, some possess magnetic fields comparable to those found in magnetars, extending for thousands and thousands of kilometers. If such a star is also rapidly rotating, then during the collapse of its core, the conservation of angular momentum further accelerates this process, much like a figure skater speeds up her spin by pulling her arms in close to her body during a pirouette. As the star's core compresses, shrinking from the size of our planet to just 12 meters across, its rotation speed increases by millions of times. Magnetic field lines, as if frozen into the collapsing plasma, twist and amplify until they reach strengths close to the theoretical limits allowed by the laws of physics. These fields become so powerful that they influence the very structure of space and time. The magnetic pressure within these extreme fields surpasses the pressure inside atomic nuclei. Field lines, stretched to their limit, accumulate enough energy to power our sun for billions of years. When these magnetic structures finally lose stability and reconnect, they release the stored energy in the form of powerful magnetic blasts, making solar flares seem like mere gentle breezes in comparison. The combination of rapid rotation and incredibly strong magnetic fields creates a cosmic dynamo exceeding anything known in the universe. Charged particles, trapped by these fields, are accelerated to energies far beyond anything achievable in the most advanced particle accelerators built by humans. Individual protons acquire enough energy to split atomic nuclei with a pure kinetic impact. These magnetorotational explosions are capable of ejecting jets of magnetized plasma at speeds close to the speed of light. Unlike the jets of ordinary gamma-ray bursts, these magnetically driven flows maintain their focus over intergalactic distances, forming beams of destruction that could sterilize planets millions of light-years away. The magnetic fields generated during these explosions are so strong that they influence the vacuum of space itself. At field strengths exceeding 10 to the 15th Gauss, the quantum vacuum begins to exhibit birefringence, splitting light into distinct polarizations and creating optical effects not observed anywhere else in the universe. Space itself acquires the properties of a unique cosmic crystal with directional characteristics. Matter subjected to these extreme magnetic fields demonstrates effects that seem impossible from ordinary perspectives. Atoms are stretched into needle-like shapes oriented along the field. Chemical bonds holding molecules together are twisted and deformed beyond recognition. Even the fundamental particles that make up atoms begin to behave in entirely new ways. The energy released in a magnetorotational supernova explosion can be hundreds of times greater than that of an ordinary supernova. The explosion produces exotic isotopes that cannot be created under any other conditions, forging elements that exist for only a few seconds before decaying into more stable forms. These cosmic alchemical laboratories create materials that push the boundaries of nuclear physics. In the vast halos surrounding every galaxy, an invisible substance known as dark matter outweighs all stars combined by 5 times. This dark matter senses gravity but does not interact with anything else we know, forming a shadow universe that dictates the structure of the cosmos while remaining invisible to our instruments. However, if dark matter particles were ever to collide with their antimatter counterparts, the result could be explosions that make supernovae seem like mere fireflies. If dark matter particles are their own antiparticles, they would completely annihilate upon collision, converting all their mass into pure energy. According to Einstein's famous equation, 1 kilogram of annihilating dark matter would release as much energy as 21 million tons of explosives, making it the most efficient energy source theoretically possible. In theory, this seems quite plausible. In the densest cores of galaxy clusters, where the concentration of dark matter reaches its maximum, these annihilation processes could trigger cascades of high-energy particles and gamma rays. The energy released could exceed the total power emitted by all the stars in that cluster, creating radiation so intense that its detection would be possible from billions of light years away. Theories suggest that dark matter particles could be much more massive than ordinary protons and neutrons, potentially containing energy equivalent to hundreds or even thousands of hydrogen atoms compressed into a single particle. When such massive particles undergo annihilation, it should lead to showers of incredibly high-energy particles, causing cascading reactions that generate exotic particles not found under normal conditions. The annihilation process could create pairs of photons with energies millions of times greater than that of visible light. These gamma rays would carry a unique signature of dark matter destruction, providing scientists with a direct window into studying the properties of this mysterious substance. The most powerful annihilation events could produce photons with energies approaching the Planck scale, where the effects of quantum gravity begin to play a significant role. If dark matter annihilation primarily occurs in high-density regions, it could create certain feedback effects that, in turn, shape the distribution of matter on cosmic scales. The released energy could heat the surrounding gas, thereby preventing its collapse and the formation of new stars. Entire regions of galaxies could be sterilized by radiation arising from dark matter annihilation in their central areas. In extreme conditions, near black holes, where dark matter density can reach incredible values, the annihilation rate could become so high that it significantly contributes to the total energy output. Such events could create observable signatures in the form of high-energy neutrinos or gamma-ray bursts, which could indicate the presence of dark matter concentrations. Some theoretical models predict that dark matter annihilation can cause chain reactions, where the released energy creates conditions favorable for further annihilation events. These cascading annihilations could deplete entire regions of space, removing dark matter and leaving behind cosmic voids filled with high-energy radiation. The search for dark matter annihilation signals has led astronomers to study the most extreme environments in the universe. Galaxy centers, where dark matter density peaks, are prime targets for detecting characteristic gamma-ray signatures of annihilation. The absence of clear signals to date indicates that either dark matter does not possess the property of self-annihilation, or this process occurs much more rarely than previously assumed. Somewhere in the vastness of space, protons are accelerated to energies that surpass anything we can achieve on Earth. These cosmic ray particles hurtle through the galaxy at 99.999% the speed of light, carrying individual energies equivalent to that of a baseball thrown at about 60 miles per hour, compressed into a single atomic nucleus. The cosmic accelerators that create these particles operate on scales and with efficiencies that make our most advanced technology seem primitive. The most energetic cosmic rays detected on Earth carry energies exceeding 10 to the power of 20 electron volts, which is more than 10 million times the energy achievable in the Large Hadron Collider. One such particle contains enough energy to briefly light a small light bulb, and all that energy is concentrated in an object smaller than a proton. When such particles collide with Earth's atmosphere, they create cascades of secondary particles that can be registered by detectors spanning thousands of square kilometers. The cosmic accelerators responsible for creating these extreme particles remain one of the greatest mysteries of astrophysics. Shockwaves from supernova explosions can accelerate particles to very high energies, but they cannot explain the origin of the most extreme cosmic rays. The electric fields required to accelerate particles to such energies must extend over millions of light years and sustain voltages exceeding 10 to the power of 20 volts. Cosmic rays, elusive messengers from the depths of space, carry the mysteries of the most powerful phenomena in the universe. These particles, from protons to atomic nuclei, hurtle through space with energies reaching incredible magnitudes, exceeding 10 to the power of 20 volts. Active galactic nuclei, fueled by voracious supermassive black holes, appear to be the most likely cosmic accelerators for these particles. Magnetic fields in the vicinity of these giants can accumulate colossal reserves of energy, releasing them in sudden and powerful bursts that accelerate particles to relativistic speeds, close to the speed of light. Plasma jets ejected by these black holes form natural particle accelerators extending for millions of light years, orders of magnitude beyond the capabilities of any human-made facility. Traveling through cosmic space, cosmic ray particles are affected by magnetic fields that deflect and scatter their trajectories, making it virtually impossible to pinpoint their exact origin. Only the most energetic particles, with energies exceeding 10 to the power of 19 electron volts, can travel in nearly straight lines through galactic magnetic fields. These ultra-high energy particles provide a unique opportunity to investigate the most extreme acceleration processes occurring in the universe. The interaction of cosmic rays with magnetic fields gives rise to some of the most fascinating phenomena in astrophysics. Spiraling around field lines, these particles emit synchrotron radiation, which spans the entire electromagnetic spectrum. The radio emission originating from our galaxy is largely due to cosmic ray electrons spiraling in the Milky Way's magnetic field. Cosmic ray acceleration can occur through various mechanisms, each operating on different scales and producing particles with different energy characteristics. Shockwave acceleration occurs when particles repeatedly cross shockwave fronts, increasing their energy with each such crossing. Magnetic reconnection can impulsively accelerate particles when twisted field lines suddenly break and reconfigure. The most extreme cosmic ray events may involve entirely different acceleration mechanisms yet to be discovered. Some theories suggest that the decay of exotic particles, remnants from the Big Bang, could generate cosmic rays with energies unattainable through ordinary acceleration. These hypothetical particles could be relics of physics beyond the standard model. The interaction of cosmic rays with gas and dust in space leads to the formation of secondary particles such as gamma rays, neutrinos, and positrons. These secondary products carry information about both the cosmic rays themselves and the environment through which they pass. Studying secondary cosmic rays has revealed the composition and structure of the interstellar medium in ways inaccessible through direct observation. In the seemingly empty space between atoms, between planets and stars, the quantum vacuum buzzes with invisible activity. Virtual particles appear and disappear in such brief moments that their existence is beyond direct observation. However, these quantum fluctuations, occurring at the smallest scales, contain enough energy to power the entire observable universe and perhaps determine the fate of reality itself. The quantum vacuum is not absolutely empty. It is filled with zero-point energy that persists even at absolute zero temperature. Every cubic centimeter of space contains virtual photons, electron-positron pairs, and countless other particle combinations that borrow energy from the vacuum and must return it before quantum mechanics detects a violation. This continuous birth and annihilation of virtual particles creates an energy density that, if it could be extracted, would surpass the mass energy of all matter in the universe. Calculations show that the energy density of quantum vacuum fluctuations should be 10 to the power of 120 times greater than the observed energy density of the universe. This colossal discrepancy, known as the cosmological constant problem, represents one of the most serious failures of theoretical physics. If these calculations were correct, space itself would be so energetically unstable that atoms could not exist. Despite the fact that virtual particles cannot be directly seen, quantum vacuum fluctuations produce tangible effects that confirm their existence. For instance, the Casimir effect demonstrates the attraction between two metallic plates placed at a minimal distance from each other, influenced by the pressure of virtual particles. The space between the plates does not allow the existence of certain wavelengths of virtual photons, creating an imbalance that generates a tiny but measurable force. Virtual particles near black hole event horizons can become real through a process discovered by Stephen Hawking. One particle of a virtual pair can be absorbed by a black hole, while the other escapes, causing the black hole to gradually evaporate. This Hawking radiation represents the transformation of vacuum energy into real particles, testifying to the immense energy contained within quantum fluctuations. In the early universe, quantum vacuum fluctuations stretched to cosmic scales during the period of inflation. These microscopic energy changes became the foundation for the formation of large-scale structure, which, evolving under gravity, formed the galaxies and galaxy clusters we observe today. Every star, planet, and living creature owes its existence to quantum fluctuations that occurred when the universe was smaller than an atom. According to some theories, our entire universe emerged from a quantum vacuum fluctuation, a fleeting deviation from non-existence that somehow became permanent. In this scenario, the Big Bang was not the beginning of time, but the moment when a virtual universe became real, borrowing energy from the quantum vacuum, which it has since been repaying through the expansion of the cosmos. The power hidden in quantum vacuum fluctuations could potentially be harnessed with advanced technologies capable of manipulating the fabric of space-time itself. Theoretical developments for extracting vacuum energy include creating negative energy densities or manipulating boundary conditions that determine which virtual particles can exist in a given region of space. If vacuum energy could be utilized, it would provide a virtually inexhaustible power source existing everywhere in the universe. A device the size of a coffee cup could potentially extract enough energy to meet the needs of human civilization for billions of years, instantly rendering all other energy sources obsolete. Beyond our observable universe, past the farthest galaxies we can ever see, lies something that transcends all the cosmic forces we have encountered. If the multiverse truly exists, then our entire universe, with all its supernovae, black holes, and gamma-ray bursts, becomes just one bubble in an infinite ocean of realities, each with its own laws of physics, its own history, and its own ultimate destiny. In the eternal inflation scenario, our Big Bang was not a unique event, but one of countless explosions continuously occurring throughout a higher dimensional space. New universes are constantly popping into existence as quantum fluctuations trigger inflation in regions of false vacuum, creating an ever-expanding tree of cosmic domains that stretches infinitely in all directions. Each universe in this multiverse could have vastly different fundamental constants. In some universes, gravity might be stronger or weaker, affecting the formation of stars and galaxies. In others, the electromagnetic force might have a different intensity, making atoms impossible or creating matter with properties unimaginable to us. The strong nuclear force could be altered, preventing nuclear fusion or allowing for the existence of elements impossible in our reality. The total energy contained within an infinite multiverse would truly be boundless, making it the ultimate manifestation of cosmic power. Every possible configuration of matter and energy, every conceivable physical law, every potential history would exist somewhere in this vast array of realities. The ability to create an infinite number of universes with infinite diversity represents the absolute pinnacle of cosmic power. Some regions of the multiverse, endowed with cosmic power, might include universes that expand indefinitely, while others collapse back into themselves in a big crunch, mirroring their Big Bang origins. Still others might oscillate between expansion and contraction, forming cyclic cosmologies that repeat endlessly. The diversity of cosmic fates within the multiverse would encompass every possible outcome allowed by mathematical calculations and the laws of physics. In some interpretations of quantum mechanics, the multiverse consists of all possible outcomes of quantum measurements existing simultaneously in parallel realities. Every time a quantum event with multiple possibilities occurs, the universe splits into separate branches, each containing its unique outcome. This quantum multiverse would continuously expand as new possibilities are realized. The anthropic principle suggests that we observe the particular combination of physical constants in our universe, because only this combination allows for the existence of observers like us. In a multiverse containing all possible combinations of physical laws, conscious beings would inevitably find themselves in universes capable of supporting consciousness, no matter how improbable such universes might be. If communication between different universes were feasible, it could provide access to boundless knowledge and resources. Technologies developed in universes with different physics might be incomprehensible by our standards, yet could offer solutions to problems we cannot even imagine. The exchange of information across the multiverse would represent the ultimate expansion of scientific knowledge. The ultimate fate of the multiverse may involve the consumption of false vacuum regions by expanding bubbles of true vacuum, creating a cosmic selection process where only the most stable vacuum states survive in the long term. This could lead to a final state where all reality converges on a single set of physical laws, bringing an end to the infinite diversity of the multiverse. We have journeyed from the quantum world to the boundless multiverse, observing forces that stretch the very limits of what reality can encompass. From the strong nuclear force binding atoms together to the possibility of infinite universes creating and destroying themselves without end, we have witnessed the manifestation of power on all conceivable scales. The most astonishing truth we have uncovered is that the universe doesn't just contain power. It is power. Every atom in your body exists because forces beyond imagination hold it together. Every star illuminating the cosmic darkness burns because nuclear forces transform matter into pure energy. Every galaxy spins through space because gravity and dark energy wage their endless battle across billions of light years. But perhaps the most profound realization is that we, as conscious observers, are not separate from these cosmic forces. We are their direct offspring. The calcium in our bones was forged in stellar explosions. The iron in our blood was scattered by dying stars. The gold in our jewelry was created when neutron stars collided in violent embraces that shook space-time itself. We are literally woven from stardust, gathered by forces so mighty they can create and destroy entire worlds. And yet, here we exist, conscious beings capable of contemplating our own cosmic origins. This is proof that the universe's greatest power may lie not in its capacity to destroy, but in its potential to create complexity, beauty, and ultimately, consciousness itself. The universe worked for 13.8 billion years to create the conditions necessary for your existence. Every force we explored, from quantum fluctuations to galactic collisions, played a role in bringing about this moment when you can grasp your place in cosmic history. In the annals of cosmic history, a breathtaking picture of creation unfolds. What then is the most impressive power in the entire universe? Perhaps it is not an isolated force, but the inexhaustible creative potential of the cosmos. Its extraordinary ability to transform ordinary hydrogen into shining stars, stars in turn into heavy elements, and elements into planets, thereby creating an arena where life and consciousness can emerge to contemplate the very forces that brought them into being. The next time you gaze up at the night sky, full of twinkling stars, remember that you are a witness to the unending confrontation between the cosmic forces that shaped everything you see. And do not forget that you, born of stardust and quantum dreams, are not merely a detached observer of this cosmic drama. You are one of its most remarkable achievements. The most powerful force in the universe may lie in its ability to know itself through beings like us. By comprehending cosmic power, we become the universe awakening to its own truly magnificent potential. Thank you for watching, friends.